In this presentation, we introduce CoWTracker, a new approach for dense point tracking. By replacing cost volumes with warping, we get a simpler head, SOTA-dense tracking, and excellent zero-shot optical flow. A quick look at recent trackers, CoWTracker, CoWTracker, and CoWTracker, shows strong progress. CoWTracker boosts occlusion robustness by reasoning over multiple tracks. CoWTracker extends 2D correlations into a 4D volume, and CoWTracker proposes a unified model for tracking all points in a video. A shared ingredient across these models is the cost volume. They compute similarity between image features across frames to match points over time. However, cost volumes come with a fundamental bottleneck. They compare every feature in one frame to every feature in another, so memory and compute scale quadratically with resolution. As a result, most trackers are forced to operate at coarse feature strides, often around 1/8 resolution, which is too coarse for thin structures, boundaries, and precise localization. This limitation shows up clearly in qualitative results. In this dense tracking example from CoWTracker, the thin roller coaster structures aren't tracked reliably. The front segment is lost and boundaries are unstable. These failures likely stem from matching at low-resolution cost volumes, which sacrifices fine detail. Here's another example shows the same resolution bottleneck. A small drone moves across the scene, but at the coarse feature stride used by cost volume trackers, the model can't track reliably. You can see the tracks drift to the background and miss the drone entirely, highlighting how coarse matching fails on small, fast-moving objects. To address this, we propose CoWTracker, tracking by warping instead of correlation. CoWTracker produces accurate dense point tracks in the wild and also generalizes well across domains, including egocentric videos, self-driving scenes, and robotic manipulation. The big change is architectural. We drop cost volumes entirely and replace matching with iterative warping, inspired by classic and recent literature in optical flow. The payoff is that once we remove cost volumes, memory scales linearly instead of quadratically, allowing us to use much high-resolution features, up to half the original resolution. This lets the tracker directly index fine appearance details, which is crucial for thin structures and accurate boundaries. Here's the high-level idea, shown as an iterative refinement loop. CoWTracker alternates between two steps. First, predict motion or tracks. Second, warp target features back toward the query frame, and repeat. Each iteration makes correspondence easier by bringing the frames into closer alignment. More concretely, the model takes a query or source frame and the full video as target frames. The tracker first predicts an initial displacement field, the model's current guess of where every query pixel moves across time. Next, we warp the target frames, or in practice, the target features, using that initial estimate. For every query location, we sample the target feature at the predicted position, aligning the target features to source frame's coordinate. Instead of searching across all candidate locations like a cost volume, we only evaluate the match implied by the current prediction. Once the targets are warped, we recompute track predictions with the warped target features and the source features. With the features roughly aligned, the model can infer how to adjust the current displacement locally. That update is produced by a spatiotemporal transformer that reasons jointly over space and time. The updated displacement field is then used to warp target features again. At this point, the targets are closer to perfect alignment, so the refinement step becomes even easier and more precise. After the second warp, we produce a third prediction. Each iteration corrects residual errors left from the previous one, gradually converging toward the true correspondence. And we continue this predict-warp-refine loop for a fixed number of iterations. Our implementation uses 5 steps, which gives most of the benefit without heavy compute. One practical note: the real model warps high-resolution features, not raw RGB, and predicts delta updates rather than full displacements. But the core loop is unchanged. Start with a guess, warp for alignment, and iteratively refine. Now let's check whether CoWTracker fixes the thin structure issues we saw earlier. Compared to CoWTracker, CoWTracker follows the roller coaster much more faithfully, especially along the thin front segment and the rails. The tracks stay coherent through viewpoint change and occlusion, instead of breaking apart or vanishing. Here's the drone example again. CoWTracker on the left struggles because the drone is barely represented at 1/8 stride. CoWTracker on the right stays attached to the drone throughout the motion, benefiting directly from high-resolution features and warping-based refinement. We also compare to the strong delta baseline. In this highly non-rigid sequence with major appearance changes, delta and CoWTracker drift during the difficult motion. CoWTracker is still able to produce a tighter and more stable tracks. The qualitative gains are also reflected in the numbers. Across average Jacquard on 4 datasets, CoWTracker ranks best overall, improving overall tracker by 1.3 points and over delta by 7.2 on average. Breaking the results into point on occlusion accuracy shows the same trend. CoWTracker achieves the best localization and the best occlusion accuracy across datasets. It not only finds correspondences more reliably but also better determines when points should be marked invisible. Remarkably, CoWTracker also transfers well to optical flow, even though we never trained on flow data. To do this, we simply treat an image pair as a 2-frame video and run the exact same model without any fine-tuning. Here's a Cintel sequence. Our predicted flow in the middle is very close to the ground truth on the right, capturing large motion and thin structures cleanly. Here's another Cintel example. Even with occlusion and background clutter, the flow stays sharp and consistent. This reinforces the idea that tracking by warping can unify point tracking and optical flow with the same model. Quantitatively, CoWTracker delivers strong zero-shot flow performance. On Cintel, it achieves about 0.8 n point error in clean split and 1.5 in final split, outperforming specialized methods. It shows similarly strong results on Kitty and Spring, despite not using any optical flow supervision. A natural question is whether removing cost volumes hurts large motion tracking. To test this, we plot n-point error against motion magnitude on Cintel and compare to see RAFT, a state-of-the-art cost volume-based optical flow model. CoWTracker has lower error across every motion bin, and the error grows more slowly with displacement. Slope 0.16 versus 0.3. At the highest motion bin, we get about 46% lower EPE, showing strong robustness to large motions even without cost volumes. To wrap up, cost volumes are powerful, but they scale quadratically and force course matching. CoWTracker replaces correlation with iterative feature warping, enabling high-resolution indexing and refinement. This yields state-of-the-art dense point tracking, stronger occlusion reasoning, and surprisingly strong zero-shot optical flow. Overall, warping-based architectures give a simple, scalable way to do dense correspondence in video.